presentation on tolerant damage tolerant composites for bi-axial loading. I want to mention that the work that I will present today was done under the supervision of Professor Otmar. So there are several biological materials like teeth or bone or deep sea glass sponges which have a quite high fracture toughness, even though their constituent materials are quite brittle. The high fracture strengths of such materials can be explained by the material inhomogeneity effect caused by the large difference in the elastic properties between the brittle bioglass and the soft protein layers in such structures. In the work of Kolednik et al., such structures were analyzed to derive design criteria for such high fracture resistant materials, where they assumed a vertically smooth Young's modulus and analyzed the crack driving force in such structures. There you can see that the crack driving force ahead of the soft interlayer increases very strong, and after it drops to its minimum when the crack reaches the center of the interlayer. The effects which are commonly known here are the undershielding and shielding effect, where the crack driving force is higher and lower than the crack driving force in the homogeneous material. This strong decrease of the crack driving force is the main cause of the high fracture resistance of such material. So, in engineering applications, surface cracks cause the most failures in the engineering applications. So in this case, we only need one single interlayer instead of such layer structures to increase the fracture strength. So under an external load, a crack would, for example, grow in parallel direction and stop after it reaches the second interface. In the work of Cittanini and Kolednik, such structure was investigated by Drazen homogeneity effect. Such structures have the disadvantage that at a bi-axial tensile load, the soft interlayer will fracture immediately. So you have no load carrying capacity for bi-axial tensile stresses. In our work, we used the design approach to use elastic inhomogeneity like voids to arrest approaching cracks from the surface, because voids have a negligible stiffness and strength, and therefore a very high potential for a high material homogeneity effect. We also looked at the effect of the void shape, where we mainly focused on elliptical voids with varying aspect ratios. And additionally, we looked how the presence of stiff particles can enhance the crack trapping in composite materials, where the crack is forced to circumvent the stiff fiber and run into the void. Stiff particles have the advantage that they provide a shielding effect as well, so a crack can arrest even ahead of a stiff particle. In this work, we will focus on mainly three loading conditions, which is defined by the bi-axial factor beta, which is B0 defines the uniaxial load case, B-1 and 1 are compressive tensile and uniform tensile load case. So the goal of this work is now to find an optimum arrangement that arrests almost every crack, provides a high fracture toughness, and maintains a high material stiffness, so keeping the void volume low. To do such an investigation, we had to have an efficient crack trajectory prediction. So it is necessary to investigate numerous amounts of crack trajectories to see if every crack really runs into our inhomogeneity. So conventional numerical methods like iterative crack extension or XDAM or certain damage models are either slow or inaccurate for our purpose. So we developed a new efficient approach, the crack trajectory interpolation method, which relies on two approximations. First, the interaction of a crack the crack propagation can be determined by the investigation of a crack and just one single void, sorry. And second approximation, that the crack propagation through a multi-void array is then, because of our linear elastic material, is then accomplished through a linear superposition. So basically the crack trajectory interpolation method has two steps. First, the first step, we develop finite element model where we determine the crack driving force JT vector by the configuration force concept using finite element model with a straight crack and just one void, and by summing up the components J far and C non-homogeneity, which are the integral of the configuration force on the external boundary and on the void interface. This is done for about 500 relative positions between crack, tip, and void. And in the next step, we use these crack trajectory, crack driving force vectors, normalize them by the J homogeneous, and these crack driving force vectors form a vector field around our void where we can very efficiently interpolate the crack trajectory for each position. So here, just shortly, you can see from the finite element results the anti-shielding zone and the shielding zone around the circular void where the crack, for example, would arise from this direction. So anti-shielding zone means the crack driving force is higher than the homogeneous material, and shielding zone means that the crack driving force is lower than in the homogeneous material. On the lower part of the diagram, you see the crack propagation direction. So the direction of the crack driving force vector, where you can see in the red areas, is where the crack J-tip vector points into the direction of the void, and the blue area means that the crack driving force vector points away from the void. So the main deflection area close to at the circular void is mainly close to its boundary. So before we went into multi-areas of voids, we analyzed the arrangement of a single void in a material to determine the trapping zone size, which means it's the zone between the center line of the void and the outermost crack that runs into the void. So, which means that within the trapping zone, every crack gets arrested, so it runs into the void. So for a circular void, we derive size for the half trapping zone size or trapping zone size in this case, for 1.85 times the void radius. Such trapping zone size can be increased if we then change the void shape, for example, into horizontal direction with a void aspect ratio of 1/4, and can even be more increased if we arrange the void in the vertical direction. I have to mention that for all these three cases, the void volume is kept constant. So we determined the trapping zone size over a certain area of void aspect ratios from 1/8 to 8, and plotted over the void aspect ratio. And we determined that also for the load cases beta minus 1 and 1, where we can conclude here, for example, that the critical load case is determined being beta minus 1, means the tensile compressive load case, which has the smallest trapping zone size. Trapping zone size for vertical voids is in any case always larger than for horizontally aligned voids, and the effect of beta has been stronger experienced for the vertical voids here, where a stronger deviation occurs between each load case. So the improvement of the fracture toughness due to crack arrest is modeled by a damage-based approach of Hillerberg. So we basically compare the fracture strength of arrested crack with the surface defect, that is, which position is determined in the step before, and compare it to the fracture strength of a crack in a homogeneous material. So we plotted the evolution of the fracture strength ratio over the aspect ratio of the void, and what we can see, for example, is that for an aspect ratio greater than 1, the fracture strength becomes dependent of the load, the bi-axiality factor. The fracture strength increase has been higher for horizontal voids, for vertical voids and for horizontal voids, and the maximum appears for an aspect ratio at about an aspect ratio of 1.5. And the best combination between increase in fracture strength and trapping zone size was determined for a void with an aspect ratio of 2, so a slightly vertical void. So after several design loops, we determined here, for example, the optimum arrangement for circular voids to arrest cracks coming from the surface. In this case, the optimum range was a staggered arrangement with a vertical distance of 3.32 times R0 and horizontal displacement of 2 times the void size, where we can achieve trapping efficiency of 69 to 100%. And also for the other load cases, beta minus 1 and 1, we reach a trapping efficiency of 100% here. To decrease the void volume even more, we can apply then elliptical voids. As we've seen before, the voids with aspect ratio 2 are the best combination of trapping zone size and fracture resistance. So with this arrangement, we obtain here also an efficiency of 100%, and also for the other load cases, we achieve a trapping efficiency of 100%. The defining load case in this section was the load case beta minus 1, that determined the distances between the voids. The elliptical voids has a somehow larger distance need a larger distance in the horizontal direction, because the main crack deflection is seen ahead of the void, not above the void for a circular void. So as a conclusion to the circular voids, we see that a lesser deviation or no deviation is observed in the trapping zone efficiency here. To analyze the presence of stiff particles in the matrix, we again looked at the crack propagation around a single stiff particle, and here we, for our purpose, 2 parameters were necessary. The parameter Ly pass, which is the closest, which defines the distance of the closest crack that circumvents the particle and propagates by the particle. Within this zone, cracks are arrested, so they cannot circumvent the particle and stay in front of the particle. And also the crack deflection of this trajectory, which is here marked as delta Ly. A few points for stiff particles, we have obtained that the bi-axial detector, for example, has seen a minor effect on our parameters here, and also a particle stiffness up to 100 has shown not so much effect on Ly pass and delta Ly. And to determine the optimum arrangement of particle and void, we just need to make an addition of these 3 parameters: the Ly pass, delta Ly, and the trapping zone size. This formula is valid just for no interaction between particle and void. This means that they have to have a larger distance between them. So, for example, here for void spacing, void aspect ratio of 2 and a particle aspect ratio of 2, we derive optimal spacing of 3.7, which means a void spacing of 7.4, which is a 51% decrease of void volume compared to the optimal void shape as shown before. So to conclude, just the results, the optimum void shape is a moderately vertical elliptical void with an aspect ratio of approximately 2. The improvement of the fracture strength and the fracture toughness of brittle materials were significantly. For this case, roughly about 5 to 12. The optimum arrangement is a staggered arrangement of these voids, where the aspect ratio, with an aspect ratio of 2, the void volume can be decreased by 5% compared to the circular void, and stiff particles with an aspect ratio of 2 can decrease the void volume even down to 53%. So I'm at the end of your questions.
Thank you very much. So questions, please. Yes, please go ahead.
Is the methodology you applied also applicable to fatigue situations with load reversal?
In general, you can couple the crack propagation to any kind of loading situation you want. So you can, for example, couple the crack extension increment to the actual crack driving force. So it means that we have a higher crack driving force, you have a higher crack growth speed, for example. It's applicable.
It's based on linear superposition.
Yeah.
Thank you. It was one more question here. Yes, please.
A rather interesting problem very nice results. But I mean, if you think of the forming of the crack, I mean, if you have a void, the stress concentration is about 3, on a free surface it's 1, so if a crack forms, it will definitely in the void. So I cannot imagine a situation that that the crack forms at the free surface and not, because if you think on fatigue, yeah, that the crack forms at all in the beginning.
It depends, for example, on the loading situation. If you, for example, think of a bending loading, where, for example, the void would be inside the material and on the outer surface the stresses are higher, may cause that like under fatigue loading, the crack will initiate rather from the surface than from the void itself. It depends. I don't know. You have to look really on every specific case on its own to really determine when it makes sense to apply such.
Okay, so thank you very much.